All right, yes, question?
Really quickly, so I saw that you put out quiz one scores. Are you going to put them out at like the same time every week? Like, for example, quiz two, is that going to be released next Friday or?
I meant to release quiz one earlier.
Okay.
I was hoping to do it with homework 0, which still hasn't been released, but there's some issues with the grading. So, yeah, and I kind of forgot. But if you're wondering, and you know, when am I going to release it, just send an email, and that'll be a good reminder for me.
Okay. Thank you.
Okay, very good. So, all right, so today is kind of an important day for understanding some really important principles in machine learning. So let's see, last time we did this kind of crazy derivation. Let's actually back up to this slide. So we're looking at a pretty general setup here. There are some features X, and there are some labels Y, and the way that the labels are related to the features is basically due to some true model function F, which in general we never know, plus here's some additive noise epsilon, and all we're saying about the noise is that it's zero mean and it has some finite variance. We would like to predict Y from X. So we come up with a model we call F hat, which is in general different than F. And our model depends on some training parameters beta. In order to set those parameters, we're going to do, we're going to somehow set them from the training data. So all we're saying here really is that these particular beta, they're determined by this training data. We think of the training data as random, so therefore the beta hats are also random. And finally, what we want to do is we want to measure the mean squared error of our prediction of Y from X. And so the mean squared error says, on average, this is a statistical average over all the training data, so all those random training features, training labels, as well as over this random test noise. So averaging over all that stuff, it's asking how good is the squared error on Y for a particular set of test features X. Okay, so that's what we want to do. And then we had this long derivation that said that quantity, that mean squared error, can be written as a sum of 3 terms. This irreducible error, which we can never really do anything about. Then we have a squared bias term. The bias tells us how close Y and Y hat, our predictions are, on average for a fixed X. And then finally we have the variance, which sort of tells you how far Y hat is from the average Y hat squared on average. So just how much does Y hat move around its average? Okay, so those are the 3 terms. And okay, so I don't think I talked about this, but so this derivation, we did this for a fixed X. So that means that this mean squared error can change as you change the test training features. But you might say, well, in practice, I don't actually know what those training features, the test features will be. I don't know what they're going to be, so I don't really care about any particular test features. I just want to know how good is this going to be on average over my average test features that I might encounter. So if you want that, you take this X-dependent quantity and you do one more average over that X, over those test features. And then we will get just the average mean squared error on Y hat. So we'll talk about that as well. There's really not too much we can do to these expressions to simplify things. We just need to take the average of this over x, or actually average of the squared bias over x, and we just need to take the average of the x conditional variance over x. So I guess notationally, if you wanted, you could write this as just variance y hat, because this expectation kind of kills this. But this one, I don't think this can be simplified really. No, can't. Okay, so that's what we found. So now I'm going to hopefully explain all this a lot better using this polynomial demo. I think this is one of the coolest demos of the semester. So this is how it goes. Let me recall, we had some pictures back here somewhere. Okay, these are good ones. So this was our polynomial experiment. So every time we run this experiment, we generate a set of random XY pairs, and for a particular hypothesized model order, in this case it's 1, we compute this least squares model. So when the model order is 1, we're computing a line. That line depends on all our training samples. So every time I do this experiment, that blue line changes a little, or green line changes a little bit, right? Because I have slightly different training data. The same thing can be done for any model order, like in this case d equals 15, except instead of a line we have a curve, and this curve is a lot more wiggly than the true red model. And of course, every time I generate a new training data set, I'm going to have a slightly different green curve. Okay, so now what we do in this experiment over here, to understand all this bias variance stuff, what we did is we did 100,000 independent experiments. Okay, ran that code 100,000 times. And I did that because if I want to compute a quantity like this, if I want to do this analytically, I have to be able to do all these expectations analytically in the variance with integrals, and that is kind of a mess, especially with the polynomial model. So we can't do that. So as a way of estimating these quantities, what I did is I essentially did what's called a Monte Carlo average, which is like a sample average over all these different combinations of x and y and everything, like 100,000 times. So it's a really good average, so we can trust it. Okay, so essentially we're really trying to evaluate that statistical expectation, the statistical variance, but I had to do it with just 100,000 averages. Okay, so in this first column, we have the situation where when we did the modeling, we used a linear model, d equals 1. Okay, so what you see here as the green line, the green line is the average, what's this? This is the average prediction given x. So let's take a particular x here. Let's imagine that we're focusing on x is 0.5. So if I want to know what is the average y hat over these 100,000 experiments when x was 0.5, that green line tells me it was right there. Okay. Now, remember that every time I did that experiment, that changed a little bit because I have a slightly different linear model. And so I also looked at the variance of my prediction given x. How much did it change around its average value? And I plotted that using these error bars. So right at that point here, you can see, or this is actually showing you the standard deviation. So it wiggled up and down with that kind of standard deviation. Okay, so when you look at these different standard deviations, one thing you notice is that you have shorter bars in the middle, longer bars on the edges. So let's see, why do you think that is? Let's see, is Nathan Becker here?
Yeah, so because how like your linear fit is doing it, is trying to make like the function go through x bar, y bar. So it kind of makes sense that the center matches, but the slope could change.
Okay. Yeah, maybe another way to say it is like, if all the line did is move straight up and down, then you would have equal error bars everywhere. But if the line tilts at all around its center, you're going to get bigger errors on the edges than in the middle. And that's what's happening. It's shifting up and down, but it's also tilting. And so that kind of is sort of an intuitive explanation for why these are a little bit bigger than these. Okay. Next question. Based on our definition of bias, let's see. So bias, just to remind you, this is the definition of bias. Is y equal to y hat on average for a particular x? Okay, so if we're focusing on this particular x is 0.5, is this model biased? Let's see, is Jacob Brees here?
Yeah.
All right, yeah, so what do you think? Is it biased or unbiased for that x?
For the x.
For x is 0.5.
I would say it is pretty biased.
Yeah, and why are you saying that?
Like it's choosing like way close to its prediction.
Okay,
How
okay, so what I was looking for is the bias, which is the difference between y hat and y, is simply the gap between the green and red. So this is the true y. This is the true y, like on average, right? Because actually the true y has noise in it. So the true y is half the time it's above this, half the time below this. But this red curve is the average true y because you're averaging out that zero mean noise. So this is the average y, right there. This is the average y hat. That's how we define the green line. So if I want to know the bias, I look at the difference between red and green, and I find that at that x, it's biased. So what about this x right here? Or what about 0? Is it biased at 0? No, right? Actually, the green and red match up perfectly. So here you can see why we were looking at this as a function of x. Because for some x, there actually might be no difference on average between the true and predicted targets, but at other x, there may be. And what we really want is that there's no difference for any x. Okay. I think inevitably you can find some x for which you kind of get lucky. That on average that for that particular x I'm getting the targets to match the truth, the target, predicted target, and true to match. But at other x maybe not. So we want to see if this is true at all x. Okay. The second question is, where do I see the variance reflected on the green curve? Well, the way we constructed this green error bar is that the error bar is just the square root of that variance. So if we're saying again, at x is 0.5, and we want to know what is the variance of our prediction, it's just how much is it wiggling around its average. Okay. This has nothing to do with the truth now. This is just how much is it varying around its average. So that's what those error bars tell us. Okay, so the the variance of our model is seen by these error bars, the green ones. And the bias is the gap between the red and green curves. And the mean squared error is the sum of that variance and the squared bias. So those two things add to give you the mean squared error. Okay, plus the irreducible error, sigma squared. Okay. Okay, so is this making sense, this picture here? So I think this picture really helps to explain what is going on in this derivation. All right, any questions on the picture? Okay, yes.
So we see that in some places the bias is positive and in others it's bias is negative.
Yes, exactly.
In expectation, does that not cancel out?
Depends what you're doing your expectation over, but like if you were doing your expectation over x, then yes, it cancels out. And that is exactly why it's not meaningful to look at the bias unless you condition on X. Because like you just pointed out, if based on the symmetry of this, the difference between the red and green, it's symmetric. So if I do an expectation, and let's say my X's are also symmetrically distributed, it would look like the bias is 0, right? But it's not. There's a persistent error. Like whenever we're at 0.5, we are persistently above the truth. Whenever minus 0.5, we're persistently below the truth. That matters. So that's why it's super important to condition when you evaluate bias. Yeah. Okay. Great. Any other questions? Okay, so let's move on to the middle column now. So in the middle column, z equals 1. Now we have d equals 3. So what's really interesting about this curve? Well, the green is right on top of the red everywhere. Okay. So what does that mean in terms of bias? Let me ask, is Sarah Hutter here? Okay, what about Jacob Isaman? What about Kevin Kim? Okay, what about Jack Lanza?
Here.
All right.
So in this case, for the d equals 3, you're not seeing a bias there, there's no difference between the red and green.
Exactly. For any x I look at, no matter what x is, oops, no matter what x is, there's no gap, which is fantastic, right? It means like on average, our predictions are always correct no matter what x is. Now that does not mean that every time I run an experiment, I'm getting the right answer. No, because even though the average prediction is correct, the instantaneous prediction is deviating from that average, and that's what these error bars show us. So here again, the error bars are a bit higher on the edges than they are in the middle, and that shows you that the variance is also dependent on x. It's not the same everywhere. But yeah, it's kind of amazing that here, in this case, d equals 3, we have no bias. And this does happen more generally. We'll talk about more situations where this can happen. Okay, any questions on this one? Yes.
Sorry, maybe I'm just completely missing something. Could you explain why it's medium variance here versus the last?
Oh yeah, I guess we didn't talk about that. So if we compare the error bars on the left and the error bars in the middle, they're a little bit taller. I don't know, right? Like look at this one. Look at this one. It's not a huge amount, but they're a little bit taller. So as we, why?
Yeah.
We will. I'll show you on the next slide. Okay. Yeah. So, but this is also a trend. It's a trend that we can see empirically here happening. Okay. Everybody good with the middle? Okay, let's move on to the right one. So in the right one, this is maybe the most interesting. So this is the case where we're using that 14-order polynomial model, which is kind of crazy. It's like way more complex than we need. It wiggles around a crazy amount. And what's happening here is, first of all, is this biased or unbiased? So let's see, is Mitchell Leroy here? What about Vincent Lin? Oh, yeah. What do you think, Vincent? Is this unbiased at d equals 14? No bias? Yeah. No bias is the same as unbiased. Yes, exactly. The green average curve is completely covering the red one. There's a little bit of a gap here, but it's basically because 100,000 wasn't enough to really make those agree. If I would have run maybe like 10 million, maybe you would have covered it up. But what's most interesting here is, as we go from here to here, the variance is going up considerably, especially around the edges, right? We have like huge variance here, crazy variances on the edges. So this is because when you compute this 14-order model, towards the edges, it is doing crazy things in trying to fit the data. And that is reflected here. Even though on average it's doing the right thing, from experiment to experiment is doing crazy things, really crazy. And this is, again, the trend. We go from low variance to medium variance to high variance as we increase that model complexity. Okay. All right, so hopefully this helps to make sense about why we're caring about these and what they mean. Any last question about these? Yes.
I mean, so why wouldn't, for our bias term, if we wouldn't want it to cancel out, why wouldn't we like square the inside of that, kind of like variance, right? Because like variance is squared, not just to like kind of weigh outliers, but also so that it doesn't cancel out.
I guess I'm not sure what you mean. So like these things just come out of a derivation. So we take this quantity, which we want, which is sort of like the main thing we want to minimize, and we just sort of rearranged it and out popped like kind of a decomposition of that into three different things. One of them, irreducible. The second, how close we are to the truth on average. Third, how close are we to our average prediction. So that's just one particular way to split this apart. And so I don't know, with that, can you clarify your question? Like,
Maybe I'll ask it.
okay, yeah.
So I have a question. So the irreducible error, would that be like when you go to the d equals 1, would that be the smallest error bar you see there? Or would you be able to see that on the plot at all?
I don't know if it's the smallest one, but it's not, I don't think it's visible in the plot because so even if, well, maybe it would be, yeah. So what I was going to say is like, even if we got this polynomial model perfectly, for every x, we're perfectly predicting the noiseless part of y. We can never predict that independent noise. So that is always there. It's unpredictable. And that is what's leading to this irreducible error term. So, so basically, yeah, I think you would see it here in terms of, let's see, would you see? No, I guess you don't see it on these plots because, so what we're showing here is this is the deviation from our average y hat. So what I'm saying is like if I came up with a model f hat that just takes the features and evaluates the polynomial, and if I fix x, I'm always going to get the same y hat. Right? So there will be no difference in my y hats. My variance will actually be 0. But the targets are moving around, and that is what is giving the irreducible error. Yeah. Yeah, this has nothing to do with the truth, with the true labels. This is purely how much the predictions are varying around their mean. Okay, great questions. Any more questions? Okay, so so to try to answer a little bit more about why the variance is increasing, we can answer that if we do a variation on our derivation that is a little bit more narrow in terms of its scope. So this derivation was extremely general. We assume nothing about f, nothing about f hat, nothing about the noise distribution, nothing about the distribution on the x's. No assumptions were made. And still we get, this decomposition. Okay, so now to make things a little bit more intuitive, let's look at a very particular situation, which is one that we've been focusing on a lot. And that is when we have the data, the true targets, are coming from a linear model. So here, there's the true model is linear. There are these true beta coefficients. There's also a true model order. And the targets are that true noiseless value plus noise. We'll now assume that the noise is Gaussian just to make the derivation a bit easier. Second, we're going to assume that our predicted model is also a linear model. However, number one, we might be using the wrong model order. We're going to use D in general. D might match D true or might not. We'll look at different cases. The other assumption we're going to make is that the betas we're using are the least squares betas, those ones in particular, not some other ones, just the least squares ones. So under these assumptions, if I have time, I'll show you the derivation, but we can do a derivation and we can come up with some pretty interesting results. Okay, so the first one is actually maybe not that interesting. It's one we've seen before. It says that if the number of training samples is less than the assumed model order plus 1, then the A matrix is wide. A transpose A is not invertible. It turns out that there's actually many different betas that are least squares. So we don't know how to even define the least square solution. It's not unique. So we'll just say, like, that's a weird case. Let's not think about that. Instead, from now on, let's focus on the case where we actually have enough data to make this A matrix square and enough samples to make this square. And in that case, let's first of all consider what happens if the assumed D is less than the true D, strictly less. In this case, you can prove that you will have bias. Okay, not surprisingly, right? There's these true coefficients. We have model coefficients that there's just not enough of them, so we're never able to really match the true model. That mismatch causes underfitting and bias. Okay. On the other hand, if I have equal to D true or more, then it turns out you can prove that our prediction is going to be unbiased. Okay, and again, this is the definition of what we mean by unbiased. It means that on average, for any x, test x, the difference between our training and test predictions our test prediction and our true test is 0 on average. Okay. So again, none of that is too surprising. It actually shows, we saw exactly that here. And in fact, this experiment here is matching even this, because if I just set these features to the jth power of xi, then I have that polynomial model. So this is like a little bit more general than the polynomial model. And in that experiment, I did use Gaussian noise in the Python code. So really everything is agreeing with what we saw there. So even when this is 14 and this is 3, it's unbiased. If this is 100 and this is 3, it's unbiased. It would be hard to see that in an experiment. You'd have to do a massive amount of averaging, but it technically is, or theoretically is, unbiased. Okay, so the fourth result is probably the most interesting. So here again, we're going to assume that we have an unbiased model. So we have enough, the hypothesized number of coefficients is greater or equal to the true one. And okay, so this is, I think the coolest result is that you can derive that the variance on average equals D plus 1 over N. Okay, so here we do need to do an average over all possible test features. If you don't do that average, you can't get this result. But on average, you can get this result. There's also sort of, for technical reasons in the proof, I'm assuming we have a lot of samples. There may be some more sophisticated proofs that can do this with less of a requirement about this. I'm not sure, but that's just how I did it. And what's most interesting is the interpretation of this. Okay, so let's say that we fix our model size, D. We fix D. We can ask the question, what happens as I collect more and more data? What happens to the quality of my outputs? Okay. So let's see, is Armin Mazad here?
Yeah.
Yeah.
Could you repeat the question?
So what happens to the quality of my mean squared error? What happens to my mean squared error as I collect more training samples? So as n increases for a fixed d. Okay, what happens to the variance?
I mean, I'm assuming, based on what we saw before, I'm assuming it goes up.
Well, okay, so we're fixing d and we're increasing n. So look at this
Yeah.
equation.
So the parameters are the same, and we're just adding more variable, more samples, right?
More samples, yeah. So what happens to this fraction as n increases?
Which is gonna get much, much smaller.
Exactly. It goes to 0, right? So that means like our variance decreases. We know that this is one of the 3 components in our mean squared error, right? So our bias is also 0 in this scenario. So we have no bias. So what we have is we have I think I'm forgetting there's one more term, which is the sigma squared. Okay. So we have that irreducible error. There's no way to get rid of that. But then there's no bias. So the other component to mean squared error is this. And we can see that this just decreases as our data set grows. So this is like an example of why in machine learning you want large data sets. Because the larger your data set for a fixed model, the performance just gets better and better and better. Okay. On the other hand, you might say, well, I have a finite data set. I don't have control over that. Someone gave me the data set and it's fixed. So now I have a choice over the model order. So what happens is I increase the model order for a fixed n. What happens to this? It goes up. So now my mean squared error goes up, not because of my bias. My bias won't go up. When d is large enough, the bias is 0, so that's fine. But my variance will go up. So this is the cost to using a model that's more complicated than you need. It's all about the variance. Every time you run the experiment, essentially, like on average, you're doing fine. The problem is that every time you run that experiment, you're farther from your average. So that's where this is killing you. Okay, so I think this is one of the more insightful results. So just here's paraphrasing words. The variance increases linearly with the number of model parameters, or it decreases inversely with the number of training samples. So this now we can finally see this bias variance trade-off. When d is really small, the problem is underfitting and bias. When d is smaller than d true, right? In that case, your variance is great because d is really small, but the bias is the issue. As you increase d, the bias, in this case, goes to 0, but now your variance starts to go up. Okay, so there's this sweet spot in the middle where your bias and your variance are both sort of minimized. Here's the picture. Okay, so mean squared error, actually. Okay, so here we have squared bias. As the model complexity like d increases, squared bias comes down. However, the variance goes up. The mean squared error is the sum of the red and the blue curves plus that fixed offset. That's the black mean squared error. So you can see there's this optimal mean squared error, which is in this Goldilocks place where you have simultaneously a good trade-off between the bias and the variance. Move to the right, variance kills you. Move to the left, bias kills you. You want to be in that middle position.
So the optimal position is not where they cross, in some other place?
This is a rough, this is just a rough sketch that I pulled from the internet. Yeah, this should probably be near where they're equal. I think it's going to depend on the exact shapes, but I think you can probably, for most smooth shapes like this, yeah, I think it should be right in the middle there. Yes.
Can you go up one slide?
Back?
All right.
Yeah.
So for that definition of bias, you do y hat minus y. On the other one, it was y minus y hat.
Okay. Yeah, good point. So I think it probably, probably you want to have the y hat here because like if you would say if y is positively biased, like you're predicting more than the target. So I think, yeah, probably we should have that switched. But it's really like what we usually care about is whether the bias is 0 or not 0. So in that case, the sign doesn't really matter too much. And when you square them, it doesn't matter. Yeah. So that's why I was a little bit sloppy there. But it's a good point. I should correct that to be consistent. Okay.
Just one quick question. So on the slide one down that we saw, when we said it was unbiased, we were saying that it equals 0, which is assuming the bias is negligible or it's actually 0?
Well, in some cases, it's exactly 0. Like in this least squares linear regression, you can prove that the bias really is exactly 0. In practice, it's not so simple. You have like the true data is generated by probably some really complicated model from nature. You're never going to fit that perfectly, so there's always going to be some bias. But if you have a really complicated, like deep neural network or something that can do almost anything, it can probably come quite close to modeling that thing in nature. Okay. All right. Great questions. Any other question on this stuff? Okay. So this is like super important. So yeah, in general, like it's not just about polynomials or least squares linear regression. It's sort of like in general, you have more complicated models, less complicated models. We'll see many, many instances of this as we go through the semester. So all this stuff holds for general models. And when you might say, like, what's the optimal one? Well, how do I choose this stuff? Well, the more complicated the model in nature is, the data generating model, the more complicated your approximate model needs to be to remove that bias. So, it's hard to say because in general, we don't exactly know how the data is truly being generated. We do know about the variance, though. As we have more and more data samples, the variance should decrease and decrease and decrease. So that's nice. Okay, great. So any other questions about bias variance trade-off? So here we see the trade-off. All right, so one other main slide for today, which is an important one. So one thing we've talked about several times throughout the semester, starting with Unit 1, is the sample mean. So we use the sample mean all over the place. We used it, for example, in RSS. We had these different, in cross-validation, we had these different folds. Each one was giving us a mean squared error. And we said, let's just average the mean squared error over our k folds. That should somehow improve the result. It should somehow reduce the variation across the folds and give us like a more correct understanding of what the true mean squared error is. So now we have sort of more of a framework to understand that in. We now talk about random variables. So here's an example, or this is a sort of a general formulation of that idea with the cross-validation. So you have some random variable z with a particular mean. We'll call that mean mu, and a particular variance v. So z is something that, in general, we don't really know this distribution. If we want to do a derivation on paper, then I have to tell you what it is, and you can do that. But in general, maybe we don't really know it. Maybe we're flipping coins to figure out how biased is a coin. We don't know the true bias. That's what we're trying to figure out. So our whole goal, let's say, initially, is to figure out what is this true mu. Or in the case of cross-validation, maybe mu is the true mean squared error, and z is, every time I do cross-validation and I look at one fold, I get some random value that's close to mu but not exactly equal to mu. Okay. So I want to figure out what is the true mean squared error. So the most popular thing to do is the sample mean. You take these different realizations of z. Let's say that there's capital N of them. So in terms of cross-validation, you would have k. Here we'll just call it n. And you just average them. You do a sample mean. Okay, and you get this thing z bar. So now, if I think about these zi's as random, z bar is also a random variable. And so now you could actually answer the question, is this estimate correct on average? So, every time I generate a particular z-bar, it's never going to exactly match mu. But if I average over experiment after experiment after experiment, I can do that expectation, and it's pretty straightforward to prove that, yes, if you average over all these experiments, you actually get that z-bar is true on average. In other words, this sample mean is an unbiased estimate of mu. Proving it is relatively straightforward. Imagine that these are random variables. Okay, we know that each of these random variables has a mean of mu. This is now a new random variable. So I want to take the expectation of this random variable. That is the same thing as the expectation of this whole thing. Now, due to the linearity of expectation, I can pull this average out, and now I just have the expectation of zi. And if I assume that these zi's are all statistically equal to this z, then those means are all mu. And finally, I'm averaging mu, and I get mu. So that's where this comes from. Okay, so this is part of the reason why this is such a popular estimator. It's correct on average. That's great. Of course, that doesn't mean that every time you compute this thing that it's correct. It's just on average it's correct. So then you might ask a second question, or let me pause. Are there any questions on this? Okay, so now you might say, well, all right, I know that this is almost never correct. So you might then ask, well, how much does it deviate from mu? So the average squared difference between z hat and mu is the variance on this z-bar. So the better the estimator, the smaller that variance, the closer z-bar is to the truth. So with a little bit longer derivation, you can derive exactly what this is. If you know the true variance on z, you can find that the variance on z-bar is this. So there's something intuitive here too. So the true variance, that's fixed. We have no control over that. But we might have control over how many things we're averaging. So we see that as I take more and more averages, the variance on z-bar shrinks to 0. And that means that z-bar, even every time I generate this thing, it gets closer and closer to the truth. So it's sort of like saying, if I'm trying to figure out that biased coin weight, and I flip this coin n times and average those things, as n goes to infinity, I will converge to the true. Okay, so on average, that's a good thing to do, but it actually says that average is itself perfect as the number of coin flips go to infinity. Okay, and now another interesting thing is we've seen this before. If you have the variance over the number of things you're averaging over, that is exactly the standard error squared. Right? The standard error was just the standard deviation, which is the square root of this, over the square root of n. So now we see why standard error came about. Why we defined it, why people use it. It's because it tells you exactly this variance, or square root of the variance, on this sample mean estimator. If you want to know how good is your sample mean, that's exactly what the standard error tells you. Okay, so that's an important thing. This now explains this standard error that was maybe a little bit mysterious where this was coming from. This is the explanation. Okay, so good time to pause. Is this making sense? Okay. Now, sometimes we want to do something more than just estimate the average value of z. We might actually want to estimate the variance itself. So, I have some random variable, z. I don't know the distribution of it. I see samples of it, zi. I know how to estimate the mean of z, but what about estimating the variance? So when we did this back in Unit 1, we said one way to do it is you take that sample mean estimate, you look at the difference between zi and that, and then you average that squared value. And notice that when we do it this way, we're using 1 over n here. And we called that the biased version of this. Okay, now we can understand what we mean by this biased version. So if you take this guy, you think, all right, imagine that zi is a random variable. So zi has this mean, this variance for all the different i's. That means that this is random. Now you can look at the mean of this. You can ask the question, is the variance that I computed correct on average? So here's the average variance. Turns out you can derive that is not quite correct. It's a little bit smaller than the true v. It's smaller by the ratio n minus 1 over n. So if n is very large, this ratio is very close to 1. It's not really an issue. Even though it's biased, it's what we call asymptotically unbiased. It's very close. But if n is a small number like 5, which often shows up in cross-validation, this is 4/5. That's a pretty big, error on your variance. So this biased estimate is maybe not something you want to use if n is really small. Okay. The derivation for this is not very difficult. I can show you if we have a little bit of time. Now, there's an alternative to this one way to compute the variance, which is simply to do something slightly different, where instead of 1 over n, we have 1 over n minus 1. It's just a small change. You can almost see it, like if I to go from here to here, all I have to do is multiply this by n over n minus 1, and I go from here to here. So when I do that multiplication of this, that multiplication comes out of the expectation, and that cancels this. And finally, you get an unbiased estimate of the variance. Okay, so this is an alternative that sometimes people like to use this because you know that what you're generating here, on average, is correct. Okay, so that's kind of the argument for doing this. On average, yeah, it's doing the right thing. This is not doing the right thing on average. Okay, so this is now an explanation for this, what we mean by biased and unbiased estimators of the variance that we talked about way back in Unit 1, and I said I would explain it, so this is the explanation. Okay. Questions on this? Okay. Now the last thing is you might say, well, all right, if I have this unbiased estimator of the variance, why would I ever consider this dumb biased one? Isn't that just worse? And the answer is, well, it kind of depends what you care about. If you care about bias as your main thing, then yes, this unbiased one is definitely the one to use. But if you care about something else like mean squared error, which is the average squared difference between our estimate and the truth, you can compute that for this original biased estimator. You get this expression. You can also compute it for this unbiased estimator. You get this expression. And it turns out that this unbiased estimator actually has a higher mean squared error than the biased one. So this is actually sort of now a defense of using the biased one. If you really care about mean squared error, you should be using the biased one. If you care about unbiasedness, then you put up with this extra mean squared error in order to get that unbiased quantity. And this is something that turns out a lot in statistics. Often there's a trade-off. If you want an unbiased estimator, you have to pay a price in variance. Your variance goes up to get that unbiasedness. If you can tolerate bias, you can actually reduce your mean squared error. So this happens a lot in a lot of cases. Okay. So all these derivation details are in a handout that is it's on the GitHub. You can find it there along with the lecture notes. Okay, so So that's the advantage of this bias estimator, lower mean squared error. Okay. Questions on this? Okay. All right, the very last thing to talk about is sort of like a segue into the next unit, which will start next week. And just to kind of step back and think about what we focused on in this unit, we were trying to decide between sets of models of this form. Do I use this, d equals 1, or do I use this, d equals 2, or do I use this, d equals 3? You can kind of see the pattern here is like, do I keep adding more or not? But in practice, that's not actually the question maybe you care about. Someone gives you like d different features, and you're more interested in answering like, should I use feature 1 or ignore it? Should I use feature 2 or ignore it? Should I ignore both feature 1 and feature 2 because they're like there's more noise in there than signal, and so it's really just confusing me. So, so that's a different question. That's not a model order selection question. That's what we call feature selection, which is which subset of the features we're given works best. Which ones do I consider? Which ones do I throw out because they're just not worth it? Okay, does that question sort of make sense? Okay, so what's more difficult about this is the number of subsets of possible features to consider is actually kind of large. So, I don't know, let's see, is Fatima? All right, so I gave you a hard one. So if you had to think about how many different subsets of features must we consider, like here we had 3 models. If I have D features and I have to do feature selection, how many different models do I have to consider?
I have D selections.
So yeah, so it's like I have D features, like in this case I have 3. So if I had 3 features, how many different subsets?
Say if I have to consider D models for each, like a feature, actually more than, because then you also want to combine multiple
Exactly.
features in one model.
Right.
Yeah.
So if I just had 3, which is more tractable, how many different subsets can I make?
Models.
Almost. One less, 8.
Oh, right, okay.
Where does that come from?
I was just doing N to the N, or D to the D.
Okay, so one way to think about it is the following. I can either use or not use this. That's 2 possibilities. On top of that, I can use or not use this. Now I have 4 possibilities, 2 squared. On top of that, I can use or not use this. So now I have 8, or d cubed. So do you see where this is going?
Yeah.
Or 2 cubed is 8. So basically, we have 2 to the power d possible subsets to consider. So, so that's where this new problem is tricky. So if you just have relatively few, maybe like 10 or less, 2 to the power 10, you might be able to consider all those. So what you would do, for each of those subsets of features, you would train a new model. You do cross-validation. You hold out some data or do k-fold or something, and you compute how well did that subset work. And you go through all those 2 to the power d possibilities, and you choose the best one. But as d grows larger, let's say like larger than 20, 2 to the power 20, and so on, is already getting crazy big, right? There's no way you can do that. And in practice, we often have, d could be hundreds, thousands, millions even. So there's just absolutely no way to look at all the possible subsets. So we have to be more clever. That's sort of the name of the game, is looking at more clever strategies for doing that feature selection. And that's going to give us an excuse to think about some other nice ideas as well. So that will be what we do next time. And until then, hope you guys have a great weekend. We'll see you on Monday.